4. Logistic function. The logistic function, also known as the sigma function, is a key component in logistic regression. In this chapter, we will see how logos relates to a logistic function and what logistic function is. The logos are the ratio of the probability that an event will occur to the probability that it will not occur. But it is the probability that an event will occur that the logistic regression estimates. Therefore, it is necessary to convert the logos into an equation that expresses the probability that an event will occur. Logistic regression uses a logistic function to express P as the probability of an event occurring. Let us now transform the logos into an expression for the probability P. First, we assume that the logos are equal to the linear combination of the predictors. Since both sides are equal, the exponential function with both sides as exponents is also equal. Here, we use the relationship between the exponential function and the logarithmic function, where the log x power of e is equal to x. Since log x represents what power of e equals x, e raised to the power of log x is equal to x. Substituting odds for x in this relationship, we see that the left side is equal to the odds. Therefore, the odds are equal to this exponential function. We are now back to the formula for modeling the odds as an exponential function. We can now write odds equal e to the zth power. Let's transform this equation to represent P. Through several steps, we can represent P by this fraction. Dividing the denominator and numerator of this fraction by e to the zth power, P is finally represented by this fraction. This fraction is the logistic function. The logos are also called the logit function, but the logit function and the logistic function are different functions. Therefore, we should be careful not to confuse them. The logistic function is also known as the sigma function. It is a key component in logistic regression. It is used to transform any real-valued number into a value between 0 and 1, which can be interpreted as a probability. Let's see the formula of logistic function. Here, sigma z represents the output of the logistic function. Z is the input to the function. E is Euler's number, approximately equal to 2.71828. Let's understand each component in more detail. First, let's focus on the input z. In the context of logistic regression, the input z is a linear combination of features and their corresponding coefficients. That is, a linear combination of predictor variables and their corresponding coefficients. The logistic function transforms z into a probability. Let's consider the meaning of z using a case of binary classification problem. In predictive analytics, we can predict whether the outcome will be success or failure. In a case of employee churn prediction, we can predict whether the outcome will be churn or not churn. We can call these problems binary classification problems, where we predict which of two possible outcomes will occur. In a binary classification problem, each possible outcome is often called a class. So, a binary classification problem has two classes, success and failure. Here, churn or not churn. The meaning and interpretation of Z can be understood in several ways. Logos, predictor importance, decision boundary in classification, and influence of multiple predictors. As noted earlier, Z, the input to the logistic function, is a linear combination of the predictors. In binary classification, this linear combination equation is modeled by logos. Therefore, we can say that the inputs to the logistic function are modeled by logos, and the exponential function is modeled by odds. So, if we assume the result consists of success and failure, we can regard the meaning of a z value as the following. When z is 0, the odds are 1 because it means e to the power of 0 equals 1, meaning the probability of success is 50%. A positive z indicates odds greater than 1, favoring success, while a negative z indicates odds less than 1, favoring failure. The coefficients beta I in z act as weights indicating the importance of each predictor in determining the outcome. A larger absolute value of a coefficient suggests a stronger impact of that predictor on the outcome. The sign of each coefficient indicates the direction of influence. A positive coefficient increases the logos of the outcome being 1, while a negative coefficient decreases it. It means if the coefficient is positive, the increase in the predictor variable enhances the probability of the success. If the coefficient is negative, the increase in the predictor lowers the probability of the success. If the coefficient is 0, the increase or decrease in the predictor does not affect the probability of the success. In binary classification, the boundary, where the probability of both classes is equal, is called the decision boundary. In other words, at the decision boundary, the probability of success is 50%, and the probability of failure is also 50%. Mathematically, this is where z is 0. As you already know, when z is 0, the odds are 1. Therefore, the probability of success is 50%. A positive z indicates odds greater than 1, favoring success, while a negative z indicates odds less than 1, favoring failure. For a given set of predictor values, if the z is greater than 0, the model predicts the outcome as class 1. If z is less than 0, it predicts class 0. Z can also be understood as influence of multiple predictors. Z aggregates the effects of all predictors, considering their respective weights. It's a single value, summarizing the evidence provided by the predictors about the likelihood of one outcome over the other. In the logistic function, the exponent of the exponential function in the denominator is minus z. Therefore, as z increases, the output of the exponential function approaches 0, and therefore, the output of the logistic function approaches 1. Conversely, as z decreases, the output of the exponential function increases, and therefore, the output of the logistic function approaches 0. This means that as z, the input value, increases, the probability of occurrence approaches 1. And as z decreases, the probability of occurrence approaches 0. This fraction structure ensures that the output of the logistic function is always between 0 and 1. As z goes to positive infinity, e to the power minus z approaches 0, making sigma z approaches 1. Conversely, as z goes to negative infinity, e to the power of minus z grows large and sigma z approaches 0. This behavior is ideal for representing probabilities. Graphically, the logistic function creates an S-shaped curve called the sigmoid curve. It starts near 0, increasing as z increases, and eventually levels off near 1. When sigma z is close to 1, it suggests a high probability of the data point belonging to the positive class. When sigma z is close to 0, it indicates a low probability of belonging to the positive class, implying a higher probability of belonging to the negative class. In logistic regression, the logistic function is used to estimate the probability that a given input point belongs to a certain class. For example, in a binary classification problem like spam detection, the logistic function can be used to estimate the probability of an email being spam based on the email's features like the frequency of certain words, the sender, etc.